Welcome to our first quantum physics video module. If you haven't taken the time to explore the life and times of the 19th century, my previous video, please pause and do so now, as it adds quite a bit to this topic. While I explored the landscape of several fields of knowledge in that video, here I would like to explore the landscape of physics at the dawn of quantum mechanics. The time was the last decade of the 19th century, and physics showed immense promise. Newtonian mechanics had been developed, and its application was ushering in a whole new era. Mechanical engineering, civil engineering, electrical engineering, material scientists, and architecture were finding innovative ways to use the knowledge of the pure sciences. Thermodynamics and fluid mechanics were growing fields, and the cherry on top was electricity and magnetism. The fields of physics could be understood by basically separating it into four sections. There was the physics of matter, which included Newtonian mechanics and chemistry. There was statistics, which could model entropy and random behavior. Thermodynamics looked at temperature and heat. Finally, understanding of a universal hydrodynamic ether was apparently growing. The ether explained propagation of electromagnetic waves as well as gravity's influence. While physicists continued to make strides in discovery, there were no major gaps in the theory, and many expected the future of physics would include simple application of known theory. If there was theoretical progress to be made, it was in understanding the ether. However, there were some cracks in this model. The speed of light, c, which was related to the nature of matter and ether, didn't quite fit. And the black-body radiation spectrum, which was related to statistics and thermodynamics. However, these were seen as small shortcomings in the existing theory that merely needed insight regarding the application of the existing theories. The Pandora's box began to open during investigation of black-body radiation. Wilhelm Wien developed a decaying exponential model of energy intensity as a function of wavelength that was roughly based on experimental data. Max Planck got involved because Wien's equations didn't quite align with experimental data as wavelength got large or small. Planck used entropy and an atomic oscillator as a starting point to develop a theoretically based equation for black-body radiation. If he pretended that the oscillations were discrete energy elements, he developed an equation that fit the experimental data. To be clear, he invented this idea because he could then make the equation fit the data. There was no theoretical justification for it. It's not too far from knowing the answer to part 3 on your test should be 17, so you make up an equation that has 17 as your answer. While it certainly would not fly in a test, it was an insightful move as a theorist. What did Planck think of this? After 6 years of working on the problem, he simply said it was an act of desperation. Most of the physics community saw energy elements as an interesting calculation tweak, while the real work to be done was in developing the physics of the ether. It took Einstein to give quantized energy the attention it deserved, as he saw the profound implications of a quantized view of energy. His early work was based on the photoelectric effect and black-body radiation as starting points for quantum mechanics. This is where we will pick up the story.